let's look at the next test, the limit comparison test. Now the limit comparison test says, let a sub n be greater than 0 and b sub n be greater than 0. Now here, your a sub n is always going to be your given series, and your b sub n is always going to be what you're going to compare it to, your known. Well, the limit comparison test says that if you can take the limit as n goes to infinity of a sub n, again that is your given, over b sub n, and that one is your known, and you end up with L, where L is a finite positive number, then they both do the same thing. They either both converge or they both diverge. So for the limit comparison test, you're still going to figure out what you compare it to, just like we did with the direct comparison test, but instead of doing the inequality, we are just going to take the limit as n goes to infinity of given divided by known, and if we end up with L, where L is a finite positive number, whatever my known series did, my given series will also do. Let's use the limit comparison test to determine the convergence or divergence of the series. So I have the sum from n equal 1 to infinity of 1 over 3 to the n minus 2. The first thing I do is figure out what to compare it to. Well, this is a number raised to a power, so it looks geometric. Since it looks like a geometric series, I'm going to compare it to a geometric series. Leading term in the numerator, 1. Leading term in the denominator, 3 to the n, making this a 1/3 to the n. That means that I'm going to compare it to the sum from n equals 0 to infinity of 1 over 3 to the n. That's geometric. We know that the absolute value of r is equal to 1/3. 1/3 is a number that is less than 1. Therefore, we know that this will converge. If we can take the limit as n goes to infinity of given divided by known, and we end up with a number that is finite and positive, then our series will also converge. The limit as n goes to infinity of your given, which is 1 over 3 to the n minus 2, divided by your known. Well, instead of writing it like this, I'm going to write it as a 1 over 3 to the n. Now, if you are dividing by a fraction, that's equivalent to multiplying by the reciprocal. So you're going to see me jump to this step often, where I just say it's the given times the reciprocal of my known. So the reciprocal of this guy is 3 to the n over 1. I'm going to skip to this step when we're doing these problems instead of writing it this way, because we're always going to need to multiply it by the reciprocal to evaluate, so it's a lot easier if we just skip to this step from the beginning. If I were to multiply, my numerator becomes 3 to the n, and my denominator stays 3 to the n minus 2. If I take the limit right now, this is infinity over infinity. So what do? I use L'Hopital's rule. Well, L'Hopital's rule says to take the derivative of the numerator. We end up with the natural log of 3 times 3 to the n. Take the derivative of the denominator, still the natural log of 3 times 3 to the n. And then clean this up and then take the derivative again. Well, everything's going to cancel, therefore all I'm left with is 1. So what is the limit as n goes to infinity of 1? Well, it's going to be 1. Well, 1 is a finite positive number. Since it's a finite positive number, we can then say that by the limit comparison test, and I'm going to write LCT for limit comparison test, our series converges. And our series converges because whatever the known series does, if we end up with a finite positive number, the given series will also do. Number 6, the sum from n equal 1 to infinity of 1 over 2 plus the square root of n. This looks like a p-series. Why does it look like a p-series? Because it's n raised to a power. What is the leading term of the numerator? 1. What's the leading term of the denominator? The square root of n. So I'm going to compare it to the sum from n equal 1 to infinity of 1 over, and instead of writing the square root of n, I'm going to write it with the rational exponent n to the 1/2. Therefore, we know here that p is equal to 1/2. Since p is equal to 1/2, and that's a number that is less than or equal to 1, we know that we are going to diverge. Now, using the limit comparison test, we take the limit as n goes to infinity of our given. Well, our given is 1 over 2 plus the square root of n divided by our known. But if we're dividing by a fraction, it's the same as multiplying by the reciprocal. I'm going to use this guy here since we already have a radical in the other one just to make it easier. So the reciprocal of 1 over the square root of n is the square root of n over 1. Multiplying, I get the limit as n goes to infinity of the square root of n over 2 plus the square root of n. Well, the limit as n goes to infinity of the square root of n over 2 plus the square root of n is currently infinity over infinity, but I know that it's really just a square root of n over a square root of n. Since it's just a square root of n over a square root of n, and I can reduce that to 1, I know that the limit as n goes to infinity there will just equal 1. Well, 1 is a finite positive number. Since it's a finite positive number, therefore by that limit comparison test, our series diverges. Why does it diverge? Because when we use the limit comparison test, we ended up with a finite positive number. So whatever the known series does, the given series also does. Number 7, what do we look like? Do we look geometric or do we look like a p-series? Well, this looks geometric because it's a number raised to a power. Now find those leading terms. Leading term of the numerator, 4 to the n. Leading term of the denominator, 5 to the n. This is really a 4 over 5 to the n. So let's compare it to the sum from n equals 0 to infinity of 4 over 5 to the n. That's a geometric series. We know that the absolute value of r is going to equal 4/5, and 4/5 is a number that is less than 1. Therefore, we know that we are going to converge. Now let's use that limit comparison test. We take the limit as n goes to infinity of your given 4 to the n over 5 to the n plus 1 divided by your known, but instead of dividing by the known, we're going to multiply by the reciprocal, and instead of writing it this way, we're going to write it this way, 5 to the n over 4 to the n. Well, I notice that a 4 to the n will cancel from numerator and denominator, and all I'm left with is the limit as n goes to infinity of 5 to the n over 5 to the n plus 1. Currently, this is infinity over infinity. And we can do the same thing that we did in the last one. We can just look at leading term over leading term, or we can continue to use L'Hopital's rule. If we were to use L'Hopital's rule, we'd get the limit as n goes to infinity of the derivative of the numerator, natural log of 5 times 5 to the n, over the derivative of the denominator, natural log of 5 times 5 to the n. Those would cancel. We'd end up with 1, and the limit as n goes to infinity of 1 is 1. 1 is a finite positive number. Therefore, by that limit comparison test, our series converges.